Good morning to all of you. How are you all? Is everything all right? Can you start the session? Is everything all right? Okay. So let's start with the second part of angular momentum. What is happening? So we gave you a problem. Have you solved this problem? So let us start with this homework problem. Consider an eigenstate of L square and Lz. So the eigenstate is given by Ln. Now A is an operator which is defined by n cap dot L, and n cap is given to you. So width we have to find out. How will you do this? Okay, let's start. So what we are given? A is equals to n cap dot L, right? So you can write it in this way, that nx Lx plus ny Ly plus nz Lz. Okay, so this is nothing but Lx nx ny nz in terms, it is given in terms of this psi, theta and phi. You are given this nx ny nz as sin theta cos phi, sin theta sin phi, sin theta cos phi, sin theta sin phi, and cos theta, right? So this will become Lx sin theta cos phi plus sin theta sin phi into ny plus, acha, not Ly, ny, this is Ly, and this is Lz cos theta. Good morning, Harry. What we have to find out? We have to find out delta A, which is defined as A square average minus A average square. So we need to find them separately. Okay, so let us first find expectation value of A. This one we are going to find. So expectation value of A will be, you see, we have A is equals to Lx sin theta cos phi plus Ly sin theta sin phi plus Lz cos theta. Okay, so expectation value of A, so it is this, okay. So you know expectation value of Lx is 0, this term is 0. expectation value of Ly, this is also 0 we know, and expectation value of Lz you know, mh cut. So this becomes mh cut cos theta, because expectation value of Lx and expectation value of Ly, they both are 0. Now let us calculate the expectation value of A square average. So A square, what will it become? It is like the component square. Okay, the way you find the square, Lx square sin square theta cos square phi plus Ly square sin square theta sin square phi plus Lz square cos square theta. Okay, so when you are calculating the expectation value of A square, so you have to take the expectation values of this Lx square, Ly square and Lz square. And what is the expectation value of Lx square? We have already given you the formula, that is h cut square by 2 times L into L plus 1 minus m square, okay, multiplied by sin square theta cos square phi. And what is the expectation value of Ly square? You know, expectation value of Lx square and Ly square are same. So here also we will have h cut square by 2 L into L plus 1 minus m square. So this sin square theta, sin square phi will be multiplied along with it. What remains? Lz square. The expectation value of Lz is mh cut, so square of it m square h cut square cos square theta. I hope this is clear till now. So if I take, let's say, this h cut square by 2 into L into L plus 1 minus m square common, and many other things can also be taken common. Let's say h cut square by 2 times L into L plus 1 minus m square. You see, sin square theta can also be taken common. You are left with, in the first term, cos square phi, in the second term sin square phi, and the third term remains as it is, m square h cut square cos square theta. Okay, now this sin square theta plus sin square phi plus cos square phi, this is 1. So you are left with let's say L into L plus 1 minus m square by 2 h cut square sin square theta plus m square h cut square cos square theta, right? So once we can find out expectation value of A and expectation value of A square, we can simply calculate delta A, which is the square root of the difference between A square average minus A average square. So we can now put the values. Expectation value of A square is this thing, L into L plus 1 minus m square by 2 times h cut square sin square theta plus m square h cut square cos square theta minus expectation value of A whole square. So m h cut cos theta we got. So this will become m square h cut square cos square theta. So these two terms are getting cancelled. What you are left with? You are left with square root of L into L plus 1 minus m square divided by 2. Let's take this h cut square sin square theta out of the root. So it becomes h cut sin theta. Okay. Now just remember one thing here, the value of the value of m lies between minus L to plus L. Clear? So look at the option. You have to find out the minimum value of delta A and maximum value of delta A. Okay. From the option it is appearing to be. Now if I talk about what is the minimum value of delta A, what is the minimum value of delta A? Can you tell me? Look, for a particular value of okay, if we consider the m values, what is the value of m you will take here so that this delta A expression becomes minimum? Tell me, Harry, Murli, Karthik, what should be the minimum value of delta A and what should be the maximum value of delta A? Can you tell me? Look, something minus m square, right? So if I choose, let's say m is equals to plus L or minus L, any value if you choose, then what will happen? It will become L square plus L minus L square. So L square is getting cancelled. So it is square root of L by 2 h cut sin theta. Okay, can I write? This one we get by choosing m is equals to plus minus L. Now what will be the maximum value? Look, if it subtracted least amount, then it will be maximum. So obviously if you take m equals to 0, then it will be greatest. So by choosing m equals to 0, we get L into L plus 1 by 2 times h cut sin theta. This one we get by choosing m is equals to 0. So what we can write? Hence, we can write that the value of delta A lies between square root of L by 2 h bar sin theta and L into L plus 1 by 2 square root h bar sin theta. And this is matching with option A. How pretty problem it is? Tell me. Is there any confusion? I think I have done each and every step and you have understood each and every step. Harry, Murli, everything is all right? If it is done, let's move on. Okay, let's move on. Let's talk about ladder operators. How ladder operators are defined. So we have J plus, so J and L you can consider them to be equivalent, okay, J and L. J plus, if you take Jx plus I Jy, then we define J plus, and J minus is Jx minus Ij. Okay, so we can calculate different commutation relation out of this. Let's say if you take Jz J plus, what will you get? You will get H cut J plus. Okay. If you take, let's say, Jz J minus, you will get minus H cut J minus. If you take, let's say, J square J plus, you will get 0, J square J minus, this is also 0. So these are some commutation relation, this J plus and J minus operators, ladder operators follow. So from this two, you can see J square J plus is 0, J square J minus is 0. What does it mean? It means J square and J plus minus can be measured simultaneously. So, you know, if they can be measured simultaneously, it means they will have common eigenstate. Okay, J square and J plus minus, you can see the commutation relation is they commute. So they can be measured simultaneously, and as a result of that, they will have a common set of eigen functions or eigenkets. So J plus, let's say the common set of eigenkete is Jm. So it is like the equivalent of L and M. J minus Jm. So where this kate Jm is the eigenkate. Okay. So this J plus, while operating on Jm, what does it produce? You see, some scaling factor times, you see, let me just write it for you, square root of J into J plus 1 minus M into M plus 1 times H cut is outside. Now you see, state J will remain same, this M, because it is J plus, M will become M plus. Now if I take this J minus, this will become J into J plus 1 minus M into, here it was M into M plus 1, here it will become minus M into M minus 1, H cut will remain, J, M will become M minus 1. So you have to remember these two relations, how ladder operator behaves. In different problems, these two formula will be used. Okay. Another formula, okay, we have already told you, but in terms of this Jm, let me tell you the way you calculated Lx square, right? The expectation value of Lx square, Ly square, here we are writing in terms of J. So it is as simple as that, half expectation value of J square. In which state? In the jm ket. Okay, so bra jm j square ket jm, okay, minus this jm, then jz square jm. So this is nothing but h cut square by 2 j into j plus 1 minus m square. This one we can write because jx square plus jy square plus jz square, we know this. J square is nothing but jx square plus jy square plus jz square. It means jx square, if I take jx square average, which is equals to jy square average, is nothing but half times j square minus jz square. So half times expectation value of j square minus expectation value of jz square. Because of that, we have calculated the expectation value of j square, and it is expectation value of jz square. Expectation value of j square is j into j plus 1 h cut square, and expectation value of jz square is m square h cut square. Is it clear, this slide, or any question is there? Chalo, let's do this problem. Consider the normalized wave function phi is equals to this. Consider the linear combination of wave function. Psi Lm is a simultaneous normalized eigenfunction of the angular momentum operators L square and Lz with eigenvalues L into L plus 1 h cut square and m h cut respectively. If phi is an eigenfunction of the operator Lx with eigenvalue h cut, then which of this is correct? Phi is an eigenfunction of the operator Lx with eigenvalue h cut. What does it mean? Lx, phi is an eigenfunction with eigenvalue h cut. So Lx phi is equals to h phi. This is given to you. Can you solve this problem? Phi is an eigenfunction of the operator Lx with eigenvalue h cut. So let us start with this. What is given to us? Phi is an eigenfunction of the operator Lx with eigenvalue h cut. So this can be written. Now we know what is Lx. Look at this. If j plus is equals to jx plus ijy and j minus is equals to jx minus iji, so from this can you write jx as half of j plus plus j minus. Can I write? If you add them, then you get, and if you subtract them, then you will get jy 1 by 2i j plus minus j minus. So if it is Lx, then what you can write? It is L plus L minus by 2 times phi is equals to h cut phi. Okay. So it is like L plus phi plus half time L minus phi is equals to h cut phi. So we need to calculate this L plus phi, L minus phi separately. So for, let's say, L plus, what we can write? L plus operating on phi. Okay, phi is given to you a1 psi 1 1 plus a2 psi 1 0 plus a3 psi 1 minus 1. Get phi a1 psi 1 1 plus a2 psi 1 0 plus a3 psi 1 minus 1. This is given to you, right? So when we apply L plus on this phi, it means this whole thing what you get? Look, L plus operating on psi 1 1. How L plus behaves? You see, L plus operating on Lm, square root of L into L plus 1 minus m into m plus 1 h cut. L plus L m plus 1. Okay. So if you have psi 1 1, so 1 into L equals to 1, m equals to 1. So this will become 0, right? Isn't it? So a1 times L plus psi 1 1, a2 times, so I am just writing another line just to make it clear for you. So the first term will be 0. What about the second term? L plus psi 1 0. So square root of L into L plus 1. So square root of it is 1 into 1 plus 1. So square root of 2, isn't it? And that minus m into m is 0, so that part is not coming, h cut. Okay, now psi L plus, so it will make m to m plus 1. So 0 was there, so it will become 1. Clear? Plus a3 L plus operating on psi 1 minus 1. So you see, if you do square root of 1 into 1 plus 1, so 2 minus 1 into minus 1 plus 1, so minus 1 plus 1, that is 0. So here also it is giving you square root of 2 h cut, and psi 1 minus 1 becomes 0. Okay, so this is a2 root 2 h cut psi 1 1 plus a3 root 2 h cut psi 1 0. Now let's calculate for L minus. L minus, look, you will practice a lot. This thing you will practice a lot, otherwise you will not able to solve problem like this in your examination. How things are going on, you need to learn. Now for L minus, minus m into m minus 1. So this is 0, but this will be root 2, right? So a1 root 2 h cut psi 1 and 1 unit less, so 0, plus a2 psi 1 0, so square root of 2 h cut psi 1 minus 1. Okay, now a3 1 minus 1, you see minus 1 plus 1 minus 1 minus 1. So what will be this value? It will be 0, right? Is it clear till now? So let us now put the values into this equation. So what you get? Therefore, half, so it becomes 1 upon root 2 times a2 h cut psi 1 1 plus 1 upon root 3 cube 2 a3 h cut psi 1 0 plus here also half, so a1 by root 2 h cut psi 1 0, this is a2 by root 2 h cut psi 1 minus 1, and this is equals to h bar phi, h bar, and what was phi? Phi was a1 psi 1 1, a2 psi 1 0, a3 psi 1 minus 1. Was it like this? Yes. Now from this you can compare on both sides. If you take psi 1 1, then you can see a2 by root 2 is equals to a1, right? Comparing both sides, we get, look, a2 by root 2 is equals to a1. So from this, a2 is equals to a1 root 2, and we also know that if psi is normalized, psi lm is a simultaneous normalized eigenfunction. So we can write mod a1 square plus a2 square plus a3 square is equals to 1. Isn't it? Or you can also find out two more relations involving a1, a2, a3, then you can get it. And we know this mod a1 square plus mod a2 square plus mod A3 square is equals to 1. So for what values of A1, A2, A3 this will be satisfied? Look, 80 is equals to A1 into root 2. Okay. Now if I take A1 is equals to half, A3 is equals to half, then A2 will become 1 upon root 2. So this is from the option actually. If you take this one, then it is matching. Otherwise you can compare. Look, this is a smart way. One relation you find out that A2 is equals to A1 times root 2. Look at the option. A2 is A1 times root 2. So if you multiply root 2, you get this one. If you multiply root, you are not getting this. So this cannot be the answer. By multiplying root 2, you are getting this, may be an option. By multiplying, so this is not the option. So this 2 is vanished. Next, by doing A1 square plus A2 square plus A3 square, you should get 1. Okay. So that is possible here in case of A. Is it clear, guys? This will become a little bit haphazard. Yes, mod, this one we wrote because you see it's a normalizer function, right? Phi. So phi equals to 1. That is why modulus of A1 square, A2 square, A3 square equals to 1, and this psi lm also simultaneously normalized. So we used here psi lm psi L prime m prime equals to delta LL prime delta mm prime. Clear? Acha, I think you need one more relation because from in the first two options we are confused. So A2 by root 2 is equals to A3. Okay, after these two relations we can say, or better if we write A3 is equals to A2 by root 2. So now we can choose that option A is the correct option. Let's move on. Try doing this problem. If Li are the components of the angular momentum operator L, then the operator I runs from 1 to 3 Li equals. Okay. What we have to do? We have to find out sum over I, which can run 1, 2, 3. Commutation of L and Li. Li is the component of L along with Li. So it is nothing but the sum of, you see, Lx, L1 if you put, so that is Lx now. Ly Lz. Can I write it? And you see, this 3 terms will give you a similar type of terms. So let us calculate one term and we can just generalize for the remaining 2. So let us start with the first one. If you want to calculate, let's say, the commutation between L and Lx, how will you write? So L has Lx I cap plus Ly j cap plus Lz k cap along with this commutation of Lx. Okay. So this will give you 2 terms, 3 terms actually. Lx I cap, Ly Lx j cap, Lz Lx k cap. Now the first term is 0. The second term Ly Lx, so it is in the opposite direction, so minus I cut Lz j cap, Lz Lx, so again it is Lz Lx, so it is in a clockwise sense, so this will become cut I cut Ly k cap. Hence it can be written as, क्या हो गया मेरे गले को? Okay, let's keep it as it is. Okay. So we have evaluated Lx. Now let's take the commutator with Lx. So taking commutator with this minus I cut Lz Lx j cap plus I cut Ly Lx k cap, and this will give you how much? Lz Lx, so I cut Ly, so minus plus, okay, and H cut square Lz Lx Ly j cap plus Ly Lx is minus I cut Lz, minus I cut plus I cut is plus H cut square k cap. So this is H cut square Ly j cap plus H cut square Lz k cap. So did you notice one thing? We took Lx and we get h cut square Ly j cap plus h cut square Lz k cap, right? Hence, if I take this commutation, let's say L, Ly, Ly. If you find this, what you gonna get? H cut square. Previously it was x, so we had y and z only. Here we have taken y, so we should get Lx I cap plus Ly. Ly is there, so Lz k cap. Isn't it? And if you take the commutation with Lz, then you should get Lx I cap plus Ly j cap, right? So now take the sum. Therefore, sum over I is equals to 1, 2, 3 sum over L, Li, Li, h cut square is taking common. You see, Lx is appearing twice, 2 times Lx. Ly is also appearing twice, 2 times Ly. Lz is also appearing twice, 2 times Lz. So 2 h cut square Lx I cap plus Ly j cap plus Lz k cap, that is vector L. 2 h cut square vector L. So we can put h cut is equals to 1. So to match the option, we can put h cut equals to 1. So that is matching with option B. Is it clear, guys? Okay, now let's talk about a very important thing, matrix representation of angular momentum. We have, I think, talked about it in matrix representation of an operator. So in that time we discussed about it a little bit. Let us now especially talk about angular momentum operator. Now we have two things. One is this j square, another one is jz. Okay, and they have, let's say, the common eigenstates of Jm. Okay, common eigenstates of Jm. So using this common eigenstate, we can create a basis. Okay, so let us write few lines so that you don't forget it later. Since j square and jz commute, the set of their common eigenstates Jm can be chosen as a basis. This basis is discrete, orthonormal, and complete. The operators j square and jz are diagonal in the basis given by their joint. So you see, j prime, m prime, j square, jm, this is j into j plus 1 h cut square. I don't know, this will be delta j prime j delta m prime m. And if I talk about, let's say, jz, it is mh cut delta j prime j delta m prime m. Now you see, when this term will be 1, did you write missing component for similar case? Where? Look at this. This term will be 1 only when j prime is equals to j, m prime is equals to m. Okay. So what does it mean? If j prime is equals to j, m prime is equals to m, so that means that is diagonal, right? Thus, the matrices representing j square and jz in the jm eigenbasis are diagonal. Their diagonal elements being equal to h cut square j into j plus 1 if j prime is equals to j, m prime is equals to m, and mh cut respectively. Yes. Now you see, if j plus and j minus would have commuted with jz, then they could also be written, in terms of this eigenbasis, and it could have been diagonal also. Now, since the operators j plus minus, they do not commute, you have seen it, do not commute with jz, and because of that they are represented in the, let's say, jm basis by matrices that are not diagonal, because they do not commute, that are not diagonal. What does it mean mathematically? Mathematically speaking, we can just write it in this way: J prime M prime J plus minus J M, this is equals to H cut square root of J into J plus 1 minus M into M plus 1 for J plus, M minus 1 for J minus. So we have written it together: delta J prime J delta. You see, J plus what does it do? It makes M prime to M plus 1. So if you need to make them equal, if M prime and M plus 1 becomes equal, then only it will be 1, otherwise it will be 0. About J minus make M to M minus 1, so it will be like this. So you see, previously it was J prime J, M prime M, so the diagonal elements were non-zero. But here, to get the non-zero element, you see, although J prime and J are there, M prime and M plus 1, M prime M minus 1, they are not diagonal actually. Okay. First line of the last slide. Since J square and Jz commute the set of their common eigenstate Jm can be chosen as a basis. This basis is discrete, orthonormal and complete. The operators Jz and J square are diagonal in the basis given by their joint with their eigenstate you can write. Is it now fine, Murli? Let's take an example. We are considering the case for, let's say, J is equals to 1. Sometimes this case is given in your examination. So J and M, we have given the value of J, so we can easily calculate the value of M. So if we have J is equals to 1, for J equals to 1, the allowed values of M are what will be the allowed values? minus 1, 0, plus 1, isn't it? Because we know minus J less equals to M less equals to plus J. So the joint eigenstates of J square and Jz are, look, eigenstate is represented by Jm, okay. So J is equals to 1 everywhere. So what will be the eigenstate of J square and Jz? 1 minus 1, this is 1, 1, 0, by writing J and M values, okay. For 1 J value, we will get 3 M values. So 3 kets will exist, 1, 1. So what will be the matrix now? J square matrix. So you see, firstly, we'll start from here. So 1 j square 1 1. So you can imagine it in this way. The way we used to write the component A11, A12, A13, A21, A22, A23, A31, 32, 33. So let's say this is 1, this is 2, this is 3. So it is 1 1. Okay, next what will you write? You can imagine it in this way. Let's say this is 1. Okay, I'm not writing, but just asking you to consider it to be 1. Just consider it to be 2, 3. So 1 1, next 1 2, 1 2. What will be 1 2? 1 1, 1 2, 1 3, 1 3. Right. Next 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. Okay. Now use this formula, use this relation. What you have? J prime m prime j square j m. It is when j prime j m prime m both are equal, then only it will give you j into j plus 1 h cut square, otherwise it will be 0. So you see, only diagonal terms will survive. If you look at it very carefully, only the diagonal terms are the terms where you will see that j prime and j m prime m both are equal. Okay. And for all other, you see, j prime and m prime, j prime j m prime m, they are not equal. And j is 1, so 1 into 1 plus 1, 2. So 2 h cut square we can take outside, 2 h cut square, and only diagonal elements will survive. 1 1 1, others will be 0. And that is the meaning of this line. You see, the matrices representing j square and jz in the jm eigenbases are diagonal. You can say diagonal. The diagonal elements being equal to j into j plus 1 h cut square. Okay, and when we calculate jz, it will be m h cut. So jz you can calculate. Do by yourself jz. Do quickly and tell me what are you getting. Can you do it for jz? Look for jz. The matrix format will remain same. Only thing which will change, in place of j square we have to write jz. 10 ket in bra 01, but you written two position in the same as ket. This one 10 ket in bra. Yes, 01, whatever position same as ket. The position is not changing. 10, it will be bra 10, ket 10. What is wrong? No, it is okay. You can write it. Here also you wrote bra 10. It is not like it will become 01. It will remain 10. The position is not changing. You either have JM while writing ket, while writing bra you write JM. It is not like MJ will come. Is it clear? Representing A22 will be correct. A22. 22 we have taken. 1010. Is there anything wrong? Not able to get it. What are you telling? Let me know if there is anything wrong in any term. Just mention the term or position where you think it is wrong, then I will check. So this will become m h cut. M is equals to 1, right? M h cut. So here it is 1 h cut, here it is 0 h cut, here it is minus 1 h cut. So if I take h cut common, you get 1, this term will be 0, this term will be minus 1, and all other terms will be 0. Okay. Okay. Murli, is there any more confusion? Or everything is under control? So I am giving you as homework, you will try at home to find out J minus and J plus. Okay. So JZ and J square I have shown you how to do. You can calculate J minus and J plus. J minus you will get h cut square root of 2, 0, 0, 0, 1, 0, 0, 0, 1, 0. By following this relation, J prime M prime J plus minus, so you can follow this relation and you will get this matrix. You will try to prove it at home. J plus h cut square root of 2, 0, 1, 0, 0, 0, 1, 0, 0, 0. Minus 1 because it is you see JZ, what is the value JZ gives? MH cut, right? For JZ it is MH cut, and for J square it is J into J plus 1 H cut square. So it depends on MH cut. Here it was decided by J value. So 1 into 1 plus 1 H cut. Here everywhere J equals to 1 was there. But here you see, here M is equals to 1. Okay, M is equals to 1, so 1 H cut. Here M equals to 0, so 0 H cut, and here M equals to minus 1, so minus 1 H cut. If we take H cut common, so here H cut, 0 H cut, minus 1 H cut, that is why minus 1 is coming. So I hope you have got pretty much idea about everything. Let's start spin algebra and Pauli spin matrices. So till now we have just talked about orbital angular momentum. Now we are going for spin. So give the heading spin algebra and Pauli spin matrices. Lot of questions come from this. Pauli spin matrices. So if I talk about spin angular momentum, the way orbital angular momentum L was having three components, Lx, Ly, Lz. Here spin angular momentum is represented by S. It will have three components, Sx, Sy and Sz. Okay, and they follow similar type of commutation relation. Means if you take the commutator between Sx and Sy, this will give you IH cut Sz. If you take the commutator between Sy and Sz, it will give you IH cut Sx. If you take the commutation between Sz and Sx, this gives you IH cut Sy. So the way L square and Lz was having eigenvalues, let's say L into L plus 1 H cut square and M H cut, here also this S square and S will have a joint eigenstate of SMS. Okay, previously it was JM or LML, now it is SMS and SZ SMS. So spin quantum number and spin magnetic quantum number, S into S plus 1 H cut square SMS. So if you have understood the orbital angular momentum part, the spin angular momentum is just a follow up, nothing much is here. The value of ms lies between minus s to plus s. Okay, here also we define the ladder operators. Here also we define the ladder operators in this way. We define S plus as Sx plus Isy and we defined S minus as Sx minus Isy. Now S plus and S minus behaves in the same way if you apply it on SMS. So it is square root of, it is like L is replaced by S, M is replaced by MS. Only if K10 can't be the bra 01 because we have to change row to column. This is joint eigenstate. You don't think that it is separate. Okay, joint eigenstate. Because J needs to be written first, then you have to write M. just imagine it in this way. We have to write J and then M. When I write it as a cat, we'll write here. When you want to write as bra, you will write here. J needs to come first, then M will come second. Okay. So it is like the way you are writing. Let me give you an example. It is like you are writing J prime J. Okay, J square M prime M. This is the format. Okay, this is the format. So if you make this 0 first, then it will become M. Sorry. Yes, that will violate now. M prime it will become. Okay. You think about it, okay, Murli? You can DM me if you have any more doubts regarding this. So spin we have defined, so it is almost defined in the similar way. Now let us talk about Pauli spin matrices. But the problem is there is no space left. Where will I write Pauli spin matrices? Pauli spin matrices. Okay. So Pauli spin operator, we have seen Sx, Sy and Sz. Pauli spin operator is defined in this way. Sx is equals to h cut by 2 sigma x. Sy is h cut by 2 sigma y, and Sz is equals to h cut by 2 sigma z, where this set of sigma matrices sigma x, sigma y and sigma z, they are called Pauli spin matrices. Sigma x, sigma y, sigma z. Sigma x, you need to remember these values 0, 1, 1, 0. Sigma y 0 minus I plus I 0, and sigma z is 1, 0, 0 minus 1. So these sigma x, sigma y, sigma z are known as Pauli spin matrices. Pauli spin matrices. Okay. Now there are very interesting properties of Pauli spin matrices. So let's explore their properties. The first property, like if you take the square, you take square of sigma x, you take square of sigma y, if you take a square of sigma z, all of them will give you identity matrix 1, 0, 0, 1. If you, let's say, calculate sigma j, sigma k plus sigma k, sigma j, then this will be 0. What does it mean? This means they anti-commute. Anti-commute is represented by this second bracket, sigma j, sigma k, anti-commutator is equals to 0, that is they anti-commute. Okay. We'll explore some other properties, but before that, let's solve this problem. If sigma is a Pauli spin matrix and n is a unit vector in the space, then sigma dot n cap square is equivalent to. Sigma dot n cap square you have to calculate. Look, sigma dot n cap, so dot product is what? Nx sigma x plus ny sigma y nz sigma z. Square means it will be multiplied with itself. So this will give you nx square sigma x square plus ny square sigma y square nz square sigma z square plus nx ny, if you take common, so you see sigma x sigma y, and from this sigma y sigma x plus, let's say ny nz. So this is sigma y sigma z plus sigma z sigma y plus nz nx sigma z sigma x sigma x sigma z. So you see sigma x square sigma y square sigma z square, we have already told you that is identity. So you have nx square plus ny square plus nz square, and sigmas are the anti-commute, right? So sigma j sigma k, the anti-commute. So this term will be 0, this term will also be 0, and this term is also 0. So nx square plus ny square plus nz square, n is a unit vector, so square of it will be 1 unity. So this will be identity. Is it clear or not? Okay, one thing I told you that they anti-commute. Okay, second property, let's say write the third property here. They anti-commute. So what will be the value if you take the commutator sigma j sigma k, let's say, this will be given by twice I epsilon j k l sigma l, where epsilon j k l is the Levi-Civita symbol, 3-dimensional Levi-Civita symbol. So if you take clockwise sense, then it is +1, anti-clockwise -1. If repetition of index is there, then that will be 0. Isn't it? epsilon jkl plus 1 for even permutation of xyz, permutation of, let's say, jkl, this is -1 for odd permutation, and it is 0 for repetition of indices. We have already told you na this Lebesgue symbol. So if you take sigma x, that will be 0. If you take sigma x, sigma y, that value will be sigma x, sigma y, so 2i sigma z, right? If you take sigma y, sigma x, that will be minus 2i sigma z. Fourth property, let's say if you take the product of sigma x and sigma y, you will get I times sigma z. Fifth, if you take the product of sigma x, sigma y, let's say sigma z, so obviously this will be I times identity. So I 0 0 I. So I think these many properties are enough for you. Let's go for another problem. If sigma x is a x component of Pauli spin matrix, then find which of the following is equivalent to 2i plus sigma x inverse. What we have to find out? 2i plus sigma x inverse. So if I take 2 common, so 2 inverse means 1 by 2 I plus sigma x by 2 inverse. So it is like 1 plus x to the power minus 1 formula. 1 plus x to the power minus 1, so 1 minus x plus x square minus x cube plus so on. Now you see sigma x, it is nothing but sigma x cube, because sigma x square is identity. So sigma x cube will be identity into sigma x, that is sigma x. Okay, if I calculate sigma x to the power 5, so sigma x cube into sigma x square, sigma x square goes to identity, so it is sigma x square is equals to, sigma x cube is sigma x. So if you just keep on doing, it will give you same value. And on the other hand, sigma x square is equals to identity, sigma x to the power 4 means sigma x square whole square, sigma x to the power 6, sigma x square to the power 3, so that is identity, and so on. So what you can write? We can write that 2i plus sigma x inverse is equals to, I am writing this one. Let's say if I take I common, so I by 2, what will you get? 1 plus sigma x square is identity again, so 1 by 2 square plus, next sigma x to the power 4 you will get by 2 to the power 4, so 1 by 2 to the power 4, and so on. Now minus sigma x by 2 common you are taking, so sigma x by 4, so what are you getting? 1 means identity, okay, 1. Next sigma x you have taken count, so sigma x square by 2 cube, so 1 by minus we have taken common, so 1 by 2 cube, sorry 2 square, because sigma x by 2 we have taken common. Now sigma x to the power 5 we will get sigma x to the power 5 by 2 to the power 5, so we will have 1 by 2 to the power 4 and so on. So what are these two series? So geometrical progression, right? 1 plus 1 by 2 square plus 1 by 2 to the power 4. This is geometrical series na, with common ratio 1 by 2 square. So if you have, let's say, a geometrical series, the sum is given by a into, if r is less than 1, so 1 minus r to the power n divided by 1 minus r. If you remember, you have read it in class 12. Okay, so here the first term is 1, a is the first term, 1 minus r is the common multiplier, you can say. So 1 to 1 by 2 square, so 1 by 2 square into 1 by 2 square, 1 by 2 to the power 4, 1 by 2 to the power into 1 by 2 square is 1 by 2 to the power 6. So this r value is 1 by 2 square whole to the power n divided by 1 minus 1 by 2 square. So what are you getting? Look, it has infinite terms. So this first term 1 by 2 square to the power n is vanishing because n is tending to infinity. So 1 by infinity is 0. So you are left with 1 by 1 minus 4, 1 minus 1 by 4. So that is 3 by 4, 4 by 3. So this thing becomes I by 2 times 4 by 3 minus sigma x by 4 into 4 by 3. So this is nothing but 2/3 identity minus 1/3 sigma x, that is matching with option A. Look, the problems are not difficult, and when you see the solution it might appear to be very easy, but if you don't practice enough, these questions will not get solved so easily. Okay, so we'll continue from here on the next day, stopping here. Any question? Anyone has? If not, then bye bye, take care. Matrices introduced in quantum mechanics specifically. Matrices introduced in quantum mechanics specifically for what purpose? Just a general question. Sometimes it is convenient. That's everything is made for convenience. Okay, because if you can somehow represent operator in matrix form, then it is easy to tackle situations. Okay, na? So you can understand it in this way. Like we have 3 types of coordinate system: Cartesian, spherical polar, and cylindrical polar. So why do we go for, let's say if you have some spherical symmetry, why do you use spherical polar coordinate? One simple answer is because of to make the calculation simple. Okay, chalo, bye.